Hello, my name's Mark Moulden. I'm the Technical Director at Organics Group, and today I've got a presentation, it's about half an hour long, to introduce you to the Organics thermal ammonia stripping process and our experiences in Hong Kong over the last couple of decades. The Organics Group is an international company that operates out of regional offices around the world. Our head office is in the UK, where Dr. Robert Eden, myself, and one or two other enterprising souls started the company some 25 years ago. We positioned ourselves as a process engineering company with a specialism in landfill gas management and pollution control, as our team had been operating in that sector already. Since then, we've opened offices in Thailand, the USA, Indonesia and Australia, to name a few, and been involved in the successful delivery of more than 500 projects around the world. Some time ago, following the successful conclusion of a relatively small landfill gas flare for Swire BFI in Hong Kong, we got into discussion with them about some problems they had that we thought we could offer a solution to. Firstly, they had very high levels of ammonia in their landfill leachate due to the large amount of animal protein that was finding its way into their landfill. Also, they had several thousand cubic meters per hour of landfill gas that they couldn't do anything useful with, such as produce electricity, due to local legislation, and so it was just being flared. In collaboration with them, we designed, manufactured and installed a new type of thermal ammonia stripping system that solved their ammonia issue and used their otherwise wasted landfill gas. That was over 20 years ago now, and since then we've successfully patented the process, and that first install is still operating. And we've also installed a further 14 or so systems into Hong Kong, with another couple being installed at the moment. Our key clients out there have been Swire, Sita, Suez and Veolia, and indeed there is now one of our thermal strippers on every active landfill in Hong Kong, as well as several of the closed ones. With introductions out of the way, onto the meat of the topic. In today's talk, I'll present an overview of the thermal stripping process, looking at some of the key components and processes in the system. However, if you take nothing else from this presentation, please at least take away these 4 summary bullet points. Number 1, ammonia can be removed from wastewater with heat alone. 2, thermal destruction on site removes ammonia completely, converting it to nitrogen and water. 3, thermal destruction can be achieved with emissions compliant to the toughest of standards. 4, where of interest, ammonia may also be captured for use. So, if those are our key messages, what makes our system better than others? Number 1, I think, is our track record that pretty much speaks for itself. 20 years of operation, and every landfill in Hong Kong has one. Ours is an electromechanical process with no bacteria involved. You can turn it on when you need it and turn it off when you're finished. There is no biology to keep alive or established before operation, just on and off. There are no significant chemical additions required. The other air stripping process that is out there is pH stripping, that requires the addition of large amounts of caustic soda or similar chemicals to increase the pH to 11 or 12, and then huge amounts of acid to bring it back at the end to a pH that's safe. Biological solutions often require the addition of large amounts of a carbon source that can be prohibitively expensive. The only addition our process needs is a few litres of anti-foam agent a day. Our site sits on a relatively small footprint, certainly when compared to the large lagoons or tanks required for most biological solutions. For example, a plant capable of around 1,500 cubic meters per day of wastewater, reducing the ammonia from 6,000 milligrams per litre on the inlet to 100 milligrams per litre on the outlet, would sit comfortably within an area of about 20 meters by 20 meters. Another benefit of it being a mechanical rather than biological process is that it is up and running quickly, taking less than 1 hour to reach operating conditions, and even this can be improved by using less recovered heat. Later, we will be looking at the potential benefits of recovering the ammonia in some form, but first let us consider the requirement to just remove and destroy the ammonia. The driver on a landfill is broadly to remove the ammonia and in the most economically efficient way possible, and then get rid of it. Our thermal ammonia strippers have been fulfilling that need for the last 2 decades by doing those two jobs in one bit of plant, putting the removal and destruction in one place. If you're going to do something with your ammonia, it will need to be stored and eventually shipped. There may be site or health and safety restrictions that would make this difficult, so oxidizing the ammonia on site makes sense. The legislation surrounding emissions to air is usually very clear, so there is no ambiguity about what is being targeted in terms of confirming the ammonia has been correctly dealt with. Combustion of waste gases is a well understood and predictable process that is simple to monitor. So if we are to thermally strip ammonia from a wastewater, what do we need to understand? Well, first perhaps we need to understand a little about the similarities the thermal removal of ammonia has with the pH-driven removal of ammonia. In both processes, we are looking to encourage the ammonium ion to lose a hydrogen atom and become gaseous ammonia. The relationship between ammonia gas and the ammonium ion is shown here. This equation is basically outlining that an ammonium ion plus a base used to raise the pH produces ammonia gas and water. We are trying to generate the same shift from ammonia to ammonia, but without the addition of a base. The graph here indicates that as the pH increases, the ratio F, which is the propensity of the ammonia to occupy the gas phase, also increases. So the reaction of the previous slide moves to the right, or more into the gaseous region. What the graph also shows is that as temperature increases, this same propensity can be achieved at a close to neutral pH. So the shift to the right, the production of ammonia gas, is achieved with temperature alone. Most people's impression of air stripping of ammonia is that it first requires a significant increase to the pH in order to liberate the ammonia gas, and then large amounts of air to strip off the ammonia. But by using heat in the process, the raising of pH is no longer required for typical wastewater streams. And critically, the amount of air we need to correctly strip this ammonia is around 1/10 of the air required in a pH stripping process, dramatically reducing the amount of energy required. As a summary of what is taking place within the ammonia stripper, there are two principal reactions happening. The first is the ammonia is liberated from the wastewater as a gas. The second is the ammonia gas is removed from the surface of the wastewater by the minimum amount of air. Once the ammonia gas is in the airstream, it can either be destroyed in a thermal destructor or recovered by means of a scrubber. We will look at the recovery options later, but first, let's look at the stripping and destruction option. This is a component layout to give you an idea of the flow of the system. This particular layout removes and destroys the ammonia and is the typical configuration we have used historically. On the right-hand side, there is a thermal oxidizer that receives fuel gas, typically landfill gas, and burns it to generate heat. Using high-temperature fans, the exhaust gas generated is drawn out of the thermal oxidizer and through a waste heat recovery unit. Here, the heat is taken from the gas and put into a high-pressure hot water circuit running at around 10 bar and 140 degrees centigrade. This high-pressure hot water is then pumped to where it is needed in the system to heat the wastewater and the stripping air as required. The incoming wastewater is shown here coming into the system on the bottom left of the image, being pumped through a heater, but it itself is being heated by the high-pressure hot water and up into the top of the stripping column. At the bottom of the stripping column, air is introduced and then into the column where the conditions are carefully controlled to ensure the interfaces between the air and the water are correct to encourage the ammonia to leave the water stream and enter the airstream. Back at the bottom of the stripping column, the now ammonia-free, or at least reduced down to about 100 milligrams per litre of ammonia, wastewater, is discharged from our plant. The now ammonia-polluted airstream is sent from the top of the stripper to the base of the thermal oxidizer, where it is used as combustion air in the combustion of the fuel gas, destroying the ammonia carried in it. So to translate that last slide into a real-life example, Here is one of the ammonia stripper lines currently in operation on the Suez-operated Wendt landfill site in Hong Kong. Tucked in the middle of the access structure, in the middle of the picture, is the stripping column itself, and in front of that, outside of the structure, is the thermal destructor. You can see the ducts that take the exhaust gas out of the thermal destructor down to the economiser, shown here in the bottom middle of the picture, and then back to the thermal destructor. In this example, only a portion of the exhaust gases are used, so returning the gases used within the economiser to the thermal destructor ensures a single point of release, making environmental monitoring easier. The heat recovered in the economiser is sent to the main process heat exchangers, typically a shell and tube wastewater heater and clean water steam generator, seen here to the left of the economiser. Along with our heat recovery heat exchangers, these units provide the system with the necessary hot wastewater and hot air to strip the ammonia in the stripping column. It's also worth noting the position here of the relatively small packing cleaning area. It's a contained concrete area with a mesh floor where the dirty packing can be pressure washed. But we'll be talking a little more about packing cleaner later, but for now just note the size of the cleaning area compared to the column size. So let's have a look at the major components that make up a typical plant. It's a thermal process that relies on heat, so let's start with the source of the heat, the thermal destructor, or as it is sometimes called, the thermal oxidizer. The thermal destructors that we use are our own design, based on our 30+ years of experience in landfill gas flares. They share the same burner cup design that our landfill gas flares use, which ensure correct mixing of primary air and keep the burn stable, but have additional features that have been introduced specifically to deal with the particular issues surrounding emission control that combustion of ammonia introduces. We'll have a little look at those features later on, but for now the important aspect of these combustors is that they are both combusting a fuel gas, in the case of landfill gas, and combusting and destroying the ammonia. The heat generated is then used to provide the energy for the process. Like all our ground flares, these thermal destructors are fully enclosed to provide a closed environment where we can guarantee that the waste gases are exposed to a known temperature for a known time. This is the retention time and is what drives the height of the units. The temperature that they run at varies from country to country and from contract to contract, and range from 850 degrees centigrade to 1200 degrees centigrade. Typically, however, they run at 1000 degrees centigrade and have a retention time of between 0.3 and 0.6 seconds. The temperature is automatically controlled by adjusting the amount of primary mixing air allowed in at the base of the unit by modulating louvers that react to the temperature. This retention time and controlled temperature ensures that we are always environmentally compliant with even the most strict legislation. And as we guarantee complete combustion of all gases within the combustion zone, there are, of course, no visible flames from the top or plume of any sort, just a heat haze. Once we've generated the heat, we need to move it to where it is needed. Obviously, the recovery of heat is critical to the process, and as a result, we've become quite expert in where best to target our heat recovery. When looking at the system as a whole, there is a balance to be struck between startup time and heat recovery. Although our primary heat recovery unit is the economiser that takes heat from the combusted gases in the thermal oxidizer, we also recover heat from the exiting process streams. For example, we have a cooling tower that transfers heat directly from the exiting wastewater into the incoming airstream. We also have a plate heat exchanger that recovers heat from the exiting wastewater, putting it into the incoming wastewater too. The incoming wastewater is further heated with a condenser that takes heat from the exiting airstream prior to being introduced to the thermal destructor. This both reuses the heat, but also reduces the thermal load on the thermal destructor by reducing the amount of moisture being carried in the ammonia-laden air that will be taken as a combustion air. Using recovered heat improves the energy efficiency of the system, but extends the startup time. So a good understanding of the customer's priorities is important. Of course, material selection, manufacturer quality control, and design are of critical importance too. The temperatures we expect some of the equipment to work at is such that the incorrect material selection can lead to serious problems. The wastewaters we treat are dirty and corrosive and have a high solids content, so the heat exchangers must either accommodate this or be easily serviceable. The main heat input to our system is from the thermal oxidizer via our waste heat economiser. The economiser is exposed to temperatures of up to 750 degrees centigrade and has a 10-bar water circuit flowing through it. Its design and specification is therefore of critical importance. We design our own economisers based on our 20 years of experience running them on dirty gas streams. Economisers are basically shell and tube heat exchangers where the hot gases go through the shell and the water goes through the tubes. The most efficient economisers use finned tubes, but we have found that these tend to block quickly, so we've developed finless economisers that are built in cassettes that allow the economisers to be reconditioned every 5 years or so, returning them to approaching as new condition. A hot gas fan takes exhaust gas from the thermal oxidizer and moves it through the economiser. The temperatures are carefully controlled to ensure the economiser does not overheat, but works at an optimum temperature. The exhaust gases then leave the economiser and are returned to the top of the thermal oxidizer, which, as I mentioned before, provides a single discharge point for all products of combustion, making monitoring of these emissions much easier. The high-pressure hot water circuit takes the heat from the economiser and feeds it where necessary. Generally, this will be to 1 or 2 heat exchangers that provide final stage heating for the process air and the wastewater. We use shell and tube heat exchangers to generate steam when necessary and as the main heater for the incoming wastewater. Again, material selection is fundamental, as we have found that longevity of service is of utmost importance. All too often, heat exchangers work well on day one, but quickly suffer from performance decline due to soiling. We design using a larger fouling factor, more appropriate to the wastewaters we treat, to ensure extended performance. But we recognise that eventually all things require cleaning, and when they do, it should not be impossible. We ensure that operation and servicing are at the heart of the design process, so our heat exchangers allow access not only to the tubes for rodding, but also to the outside of the tube bundle. Where possible, we manufacture everything in stainless steel, as we found that protective coats on cheaper steels get easily damaged in cleaning. The last bespoke heat exchanger we use is the condenser. The condenser is essentially a low temperature economiser, but a lot of the heat that is being recovered is latent rather than sensible. The ammoniated air that leaves the stripper is saturated and hot. By transferring the heat into the incoming leachate, we obviously save energy, but we are also reducing the amount of water being taken through to the thermal destructor. The ability of air to carry water increases as it gets hotter, so the hotter the ammoniated air, the higher the load on the thermal destructor. The condenser, which is also made of stainless steel to avoid corrosion, drops the temperature of the exiting ammoniated air, and water that is condensed out drops to the bottom of the thermal oxidizer, where it's pumped away. We are looking in particular at the destruction of ammonia, and we know the ammonia is destroyed in the thermal destructor. As I mentioned earlier, we have introduced some bespoke features into the thermal destructor to deal with the very specific issue of correctly combusting ammonia. To achieve environmental compliance with the various legislations around the world, it is very important to be able to closely control the amount of NOx that is produced when ammonia burns. Ammonia has 2 combustion possibilities. One produces nitrogen and water, and the other produces the pollutant nitric oxide. Equation B here should only happen in the presence of certain catalysts, but experience has shown that even if a small amount of the ammonia follows this path, then emissions test will be failed. Emissions limits for NOx are typically around 150 milligrams per normal cubic meter at a 3% oxygen reference, so very tight. Along with NOx, other species being monitored are usually ammonia, methane, carbon monoxide, oxygen, SOx, and so on. Emission compliance requires the thermal oxidizer to be able to be adjusted so that the ammonia combusts along path A and not path B, reliably and without fluctuation. To ensure this, we have various aspects of the combustion that we can tune to suit the gas and site conditions. We can adjust whether the fuel gas is introduced all at one level or that we stage the burn over two levels. We can balance how the ammoniated air is introduced to the thermal oxidizer, either below the burn, where it will be mainly primary combustion air, or during the burn, where it will be mainly secondary and tertiary air. Any additional primary air we allow into the thermal destructor is very closely controlled so as to keep the combustion temperature within a very narrow band. We have found that by straying by as little as 40 degrees centigrade from the ideal combustion temperature, we can lead to high levels NOx on our exhaust stream. And finally, we have the capability to recirculate some of the exhaust gas back into the base of the thermal destructor. This allows the exhaust gas to be used to keep the temperature within acceptable limits, but without introducing the additional oxygen that atmospheric air would introduce. Using the exhaust gas as cooling gas reduces the amount of additional oxygen available, and so reduces the possibility of NOx forming, whether that be high temperature NOx or ammonia-related NOx. We have looked at the main components in the system and touched on the chemistry involved. I've said repeatedly now that this is a thermal process, but what sort of heat can be used? Even with the best heat recovery in the world, we would still need a heat source of some sort. Historically, we have used landfill gas as biogas from an anaerobic digester. If the ammonia has to be destroyed, then we would still need a fuel gas of some sort, as we need to generate 850 degrees C plus to ensure complete destruction of the ammonia. If we are going to recover the ammonia rather than destroy it, then we can use a waste heat source to fuel the process from perhaps gas engines on site or spare steam from some other system on site. To give you an idea of the sort of heat load required, it takes about 50 megajoules per kilogram of ammonia removed. Or in terms of biogas, at say 60% methane, you would need around 250 cubic meters an hour of biogas to treat around 500 cubic meters a day of wastewater and destroy the ammonia produced. Obviously, the higher the flow rate, the more heat is needed, but it is worth noting that our system gets more efficient the higher the ammonia concentration on the inlet. Alternatively, that same 500 cubic meters a day could use the waste heat from, say, two 1 megawatt engines, if there's a CHP nearby. We can use the heat generated from the exhaust and also utilize the heat from the water jacket. If there are other processes on site, then perhaps they are generating excess heat that we can tap into as well. When it comes to operation of the system, we have learned that although the theory is relatively simple, ensuring the correct conditions are maintained is a very involved process. The theory says that if you heat the wastewater to the right temperature and pass enough air over it, you can remove the ammonia from the water. In practice, this requires some hard-won practical experience. We have already talked about the importance of using an appropriate heat exchanger on the dirty water and the importance of being very energy efficient. But within the stripper column itself, it is critical to ensure the two streams of water and air interact correctly. The liquid distribution must be good enough to ensure the whole width of the column is used, but robust enough not to block. We have developed our own trough and notch distribution that has stood the test of time, and our redistribution systems that prevent the liquid from moving to the walls has allowed the columns to be as tall as we need them to be. Our air heating system is also unique with its external mixing duct to ensure the most efficient use of steam. Then, once the two streams are correctly heated and distributed, we will spend a lot of time developing and establishing the correct packing material that provides the best surface area to volume ratio without blocking. I mentioned earlier that the only chemical we do add is an anti-foaming agent. This is to prevent foaming in the column that can lead to streaming of the wastewater through a foaming area, but the additional back pressure tends to make the air stream around that foam and not interact with the water, leading to poor stripping results. Correctly understanding the critical importance of maintaining temperature throughout the column has allowed us to insulate where required and introduce heat where required. We have worked closely with the operators over the years, and we are constantly getting feedback from them and feeding those lessons that we get into the design team so that each generation of plant is better than the last. Having said all that, for the operator, running the system is simple. The system itself is fully automatic. Push the green button and it runs through its startup procedure and tells you when it's ready to discharge. It then monitors critical temperatures and adjusts itself accordingly, and will safely shut down if a parameter moves out of specification and is unable to control it itself. We have learned that as long as certain key parameters are maintained, then the stripping will work repeatably with only spot checks on the outlet ammonia concentration result typically required. The system uses an HMI display to show the system information and to allow the operator to make adjustments to flow rates, etc. The operator will typically share other site duties, and any competent operator could be trained to run the system in a day or two. As I mentioned earlier, the startup time is quick, usually takes less than an hour, and the system typically then runs 24 hours a day for weeks at a time. By monitoring heat exchange and stripping performance, the service interval can be established and varies from site to site. Once the service interval has been established, what does it entail? Typically, the service is required every 3 or 4 months and will take around 2 to 3 days. The bulk of the work is in removing the dirty packing and replacing it with clean packing. Most sites hold a complete set of packing on site that they clean at convenient times while the plant is running, so that it is ready for use at the next service. The packing cleaning is often done in bespoke contained areas like the one I highlighted earlier in this presentation. The packing is usually mechanically cleaned with pressure washers, as the dirt on the packing usually takes the form of a relatively hard carbonate buildup that comes off the polypropylene packing when pressure washed. One site has the luxury of duty standby stripping columns, as they cannot afford to not have stripping capacity due to storage issues on site. Because they have duty standby columns, they adapted an approach where one column that is in standby, they would run a dilute acid wash through it, reducing the need for packing removal. This has worked very well and is certainly something worth looking onto if it is felt that the packing cleaning might be too arduous. Other work involves cleaning filters that protect pumps and cleaning any affected heat exchangers. It is not the case that all heat exchangers need cleaning every service, but most sites identify one exchanger to clean at each shutdown, so that typically the heat exchangers are cleaned about once every 18 months or so. Other tasks in the service are typical of any site plant and include greasing motors, checking belts for tightness, ensuring bolts are tight, and so on. When we look at operating requirements, we have to assume a pretty broad brush, as there are many options and issues that are site-specific. But generally speaking, single line sizes range from 100 to 5,000 cubic meters per day. It is a modular system, so if we need more capacity, we can just put an extra one on the back end. For those systems, the electrical requirements are approximately 75 kilowatts for the 100 cubic meters a day, up to around 300 kilowatts for the 5,000 cubic meters a day. There is an amount of make-up water needed if we're using steam in the system. Of course, we need a source of heat. And lastly, you need some manpower, which we've talked about already. So here are a couple of examples of our larger ammonia strippers and destructors. This one was our first system installed in 1988. The original unit comprises the equipment between the two thermal destructors on the right-hand side and was 2 lines that mirrored each other. You can see the white ceramic lining of the thermal destructors here, good up to about 1400 degrees centigrade. Commissioning the unit was a steep learning curve, but led to all the strippers in Hong Kong. The unit in the middle of the screen is line 3, installed around 2016, and is a self-contained, fully independent line, sized at around 1,400 cubic meters per day. If I could show you a similar picture of that same site today, you would see line 4 installed just beyond those tanks. It was only completed in March this year, which is when I had to leave site due to the current world lockdown. I'm hoping to get back there soon and get you some better pictures. This second example is of a large flow single line unit in a site near Chung Kwan O in Hong Kong on a landfill operated by Veolia. This particular system was retrofitted into the treatment facility they already had and replaced an SBR that was in that spot previously. It requires some careful planning, taking into consideration the existing footprint available, but it ended up fitting quite nicely. The system removes over 8 tonnes of ammonia per day and achieves a removal rate of over 97%. We are currently building a second line at this site, as the extension licence that was being given to the landfill operator means that this area will soon be covered with waste. They need to maintain leachate treatment capabilities at all times. That means that a new line must be constructed and commissioned before they can turn off the old line and clear the area ready for tipping. We've looked so far at the removal and destruction of ammonia, but I did say earlier that we would have a quick look at ammonia recovery options. Ammonia is obviously a valuable resource and is used in many applications around the world. And it was pointed out to me recently that we use around 3% of the world's energy making ammonia, so the market is huge. It was further pointed out that we use another 1.5% of the world's energy destroying it, so obviously recovering waste ammonia makes a great deal of sense. It's used in everything from fertilizer to cleaning products, from plastic production to refrigeration. Our system presents 3 basic options for recovery. The most appropriate for any site will depend on which market is closest to them, as the cost of shipping plays a part if the market is too far away. We can recover the ammonia as a salt, either ammonium phosphate or ammonium sulfate, for use directly as a fertilizer. However, this option does require storage and movement of either phosphoric or sulfuric acid, depending on the salt, and does depend on the market for the fertilizer being relatively close and reliable. A more sensible option, and certainly the one we recommend for most customers, is to produce ammonium hydroxide or aqueous ammonia. This can be produced from 10 to 25% solutions and is in the form in which most markets will want their ammonia. The third option is to process the aqueous ammonia further to produce anhydrous ammonia, but this is an involved process with much more equipment and requires storage at either high pressure or very low temperature, so it does have its complications. And so to my preferred option, option 2, the production of ammonium hydroxide. Shown here is a simple process flow that summarises the process. The stripper column on the left is the standard stripper column that I've been talking about so far. The difference comes with what we do with the ammoniated air. When we are destroying the ammonia, this air is fed into the base of the thermal destructor for destruction as primary or secondary combustion air. Here, the ammoniated air is instead fed into a second column, a scrubbing column, that has circulating within it a cold water flow. Ammonia is very soluble in water, and particularly in cold water. The air leaves the scrubbing column clean enough to return to the ammonia stripper and be used again as stripping air. The ammonia that is now dissolved in the cold water is a dilute ammonium hydroxide and can be further processed to create a specific aqueous concentration, or all the way to anhydrous or pure ammonia. Once you have your dilute ammonia solution, you can put it through a third column that contains within the top of it a reflux condenser. If you have your outtake from after the cooler in the top right of the process flow here, then you can take out ammonium hydroxide, that it is at a concentration that is dictated by the running temperature of the rectifier. If you allow the process to run all the way to the end, all the water is removed and you get pure ammonia gas, which can be either compressed or cooled to get the ammonia into a more easy form, a liquid form to store. At an industrial scale, it is most efficient to generate an aqueous ammonia at between 15 and 20%. Concentrations of approaching 30% are possible, but become quite energy intensive. This is why it is important to understand where and what the customer for your ammonia requires, and also the price they're willing to pay. Once this is all understood, the degree of processing that is required, and hence the cost of plant, can be established in an economic model. My final slide is of our stripper at ORRC in Hong Kong. It is unusual in two regards. Number one, it is taking ammonia-rich wastewater from an anaerobic digester rather than a landfill. And second, it was designed to use biogas from the AD system that could be used to generate revenue from electricity generation. You can see the generators in the foreground here in the blue containers. The revenue from the electricity is an important part of the economic viability of the plant as a whole. But nonetheless, it was demonstrated that the improvements to efficiency from removing the ammonia, combined with the cost of getting the ammonia treated off-site, meant that giving us the 250 cubic meters an hour of biogas required to run the stripper and destroy the ammonia made economic sense. This demonstrates that thermal ammonia stripping is no longer the preserve of Hong Kong with its unique combination of free heat and high ammonia that allowed us to develop this technology. There is so much focus on ammonia now, and we have improved the efficiency of our equipment to such an extent that now they make economic sense in a wider market. I'm often asked if the technology is 20 years old, used by some of the biggest names in the waste industry, installed at all the landfills in a highly regulated place in Hong Kong, why is it not being used everywhere? The answer is that only now is the climate right. We have improved our efficiencies to an extent where we make economic sense. The world is focusing more and more on ammonia, and now we can access that market by recovering the ammonia too. And when we recover the ammonia, we can run off waste heat. The potential of recovering ammonia from our waste streams is very exciting. Now, thanks to our latest plant, it is a genuinely attractive economic and environmental proposition. Right, that's the end of the presentation. I hope you found it informative and took something from it. If you have any questions, then please do contact us on the emails above, and also visit our web address for more information on any other processes you might find of interest. Thank you very much.